Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be working through a group problem covering over some of the concepts we've discussed in class on heat transfer rates. Specifically in our video today, we'll look at the heat loss through windows in a house, look at how to calculate the cost for the amount of heat that we're losing, and also discuss what some possible solutions would be for more of an energy efficient approach. As always, the work that we're going to be doing is available in hard copy form on Canvas. There's also a key available there as well. This is specifically group problem 7C if you're looking for those items out on Canvas. So here we will be taking some time to work through group problem 7C. I am going to be working through the group problem as if you are looking at the problem statements itself. You'll notice that the problem will not show up here. That will be a plenty of room to do the work that we need. But if you would like a copy of the problem, make sure to check Canvas or get one from class. So here's what we're going to be doing today. As I mentioned, we'll be looking at the heat transfer rate through a window, and then we'll be scaling that up to determine how much money we would be paying for the energy that we're losing, and then how to determine some energy efficient solutions. So really, part A of what we're going to be doing is looking at a heat transfer rate for something like a window. And what we've been doing in class, the way that we look at heat transfer rates is expressed by the following equation. The thermal conductivity of our material multiplied by what we call A, the contact area, multiplied by the temperature difference between the hot area and the cold area, divided by L, the length that the heat must travel, or typically the thickness of the material. So here in the problem statement, we're actually given a lot of the information that we need to begin. We're told the material we're looking at is glass, which has a set thermal conductivity. We're told the dimensions of the window, which we can use to find the area. We're also told the warm inside temperature and the cold outside temperature that we're dealing with. We're also told the thickness of our window, all of which are values that will show up in our heat transfer rate equation. So we are told here that our thermal conductivity, which is our K variable, is 0.96 watts per meter degree Celsius. And again, that's a value that is set for most materials. Right? As long as we know the material we're dealing with, it's really a pretty easy thing to do to find the thermal conductivity. That's values that we could do any research on. We're told the window has dimensions of, I believe, 0.9 meters by 1.1 meters. So a bit of a rectangular shape. 0.9 by 1.1. We're told the temperature inside of our house, which is what we're looking at, is 20 degrees Celsius. The cold air outside is about 2 degrees Celsius. So the delta T, or difference in those temperatures, would be 18 degrees Celsius. And we're told that our window here is about half of an inch thick. An inch is about 2.5 centimeters. So if we cut that in half and then convert to meters, it would be about 0.0125 meters. Now again, if you're looking at the problem statement, all of these numbers are given to you. So let's go ahead and use our equation to find our heat transfer rate. 0.96 multiplied by 0.9 by 1.1 multiplied by 18 divided by 0.0125. We're given about 1369 would be our value. And the units here, if we were to notice the degrees Celsius would cancel out, meters squared over meters, so the meter units would cancel out, we'll be left with watts, which we can also express as 1369 joules per second. A heat transfer rate is really measuring the movement of energy over time, which is kind of similar to what we've talked about with our equation for power. So here, I'm going to leave it in joules per second because what we'll be doing next, we'll be taking this value and scaling that up to the energy we lose in an entire month. But here's how we would find just our base heat transfer rate. Now, part B of this problem is going to ask us to determine how much energy we're losing in a month of time. So I'm going to take the value that I have from part A, 1369 joules per second, and we're just going to do some conversions with time values here. So seconds, I need to get this up to months. I don't know what the conversion from seconds to months is off the top of my head, but I do know 60 seconds would be equivalent to 1 minute. About 60 minutes per 1 hour. We've got 24 hours in 1 day. And then from here, well, not every month has the same amount of days. Let's go ahead and assume, I believe it says even in the problem statement, to assume we're dealing with a 30-day month. So we're just going to now take our value and convert from joules per second to joules per month. So 1369 by 60, multiplied by 60, multiplied by 24, and then by 30. We're going to get a pretty large value here, so I'm going to go ahead and write this in scientific notation. It's about 3.55 times 10 to the 9th power joules per month. Now again, that's not necessarily what you'll see in your calculator. It might look something a little bit like 3, 5, 4, 8, 4, 4, a bunch of numbers. But given that we don't actually know all of those values to the degree that our calculator shows them to us, we're going to go ahead and just write this in scientific notation, rounded to about 3.55 times 10 to the 9th power. Now the next part of our problem is going to look at calculating the cost for the amount of energy we're losing. So we're told in part C that we have 10 windows in our house. So first I'm going to take this value, 3.55 times 10 to the 9th power joules per month, and I'm just going to multiply by 10. The reason why is that we have 10 windows in our house, as we're assuming the dimensions are the same, the temperatures are the same, we're just going to take our rate and multiply by 10, which is going to give us really 3.55 now, multiplied by 10 to the 10th power, joules per month. Okay, so now the next part of our problem says this. We're given a rate of how much money we pay for a certain number of joules, and we want to calculate how much money we're going to spend if we're losing this much energy in our house. So here's what I know. Technically, I could multiply this by 1, because I'm dealing with 1 month of time here, just so I know I really have this many joules of energy that I lose in the time frame that we're looking at, 1 month. So I'm going to take that number, 3.55 times 10 to the 10th power joules, and I'm going to use the rate that we're given. We're told we spend about $1 for every 10 to the 8th joules. So here's how I would represent that. I have joules in my numerator, so I'm going to put units of joules in my denominator so I can make sure my units cancel out appropriately. And I'm told for every 1 times 10 to the 8th joules we use, that's going to cost $1. Now, that number, if you know much about heating bills, is going to fluctuate depending on where you live, as well as what time of year it is. But that's a number that's a good approximation for about this time of year in Oklahoma. Now again, that's not something that you would be required to memorize. It's something that, again, it's not always a set value, it's something that can fluctuate. So I've got joules over joules. So I'll take my value, 3.55 times 10 to the 10th power, and I'll divide by 1 times 10 to the 8th. By 1 times 10 to the 8th. I end up getting about 355. So that would tell me that based on the dimensions of the windows I have, based on the material those windows are made out of, the glass, based on the thickness of our window, as well as the inside and outside temperatures, I would be spending about $355 per month on the energy lost through all 10 windows. Now, if you know anything about a heating bill, you'll know that's a pretty high value. That's a lot of money to be spending. And so you might think, well, is that number realistic? Is it wrong? Well, no, not necessarily, but we need to put that number in context. This number would describe very standard, really older types of windows. Most windows that you probably have in your home or wherever you live don't actually have one single pane of glass. Most of them are double pane glass, and that's what we're going to look at here in just a moment. So that number is very high, but these are for very older styles of windows, which most people don't actually have anymore. So looking at the backside of the group problem, we're given a few different windows to look at. These here are actually windows that have a small air pocket in between, and that air pocket is designed to drop down the heat transfer rate, make it harder for the heat to move through the window so we're not losing as much energy. Now there are 3 different models there. I'm just going to choose one. We've got Model 1, which deals with an actual pocket of air, Model 2, which has a pocket of argon, and Model 3, which has a pocket of krypton. Oftentimes, noble gases or inert gases are good materials to use for these types of energy-efficient windows because they're very non-reactive. So let's just choose Model 2, argon. Right? Really, we could choose any one of these, but let's choose Model 2. So here in Part D, what we'll do is we'll look at finding the new heat transfer rate for this other model. Again, we're not going to look at every model, but let's just say we choose one of them, model number 2. So let's find the heat transfer rate for this model. I'll call this heat transfer rate 2, our second one. We've got our thermal conductivity, K. We're told for argon is 0.016. You might notice off the bat that number is going to appear to be much lower than the value we dealt with earlier for the glass. We're told here to assume that the windows are the same dimension, assuming that we just take the old windows we had and replace them with these new windows. The dimensions would probably be roughly the same, 0.9 meters by 1.1 meter. And then we'll assume, we're told here, that the air inside and outside is roughly about the same temperature. So 20 degrees inside, kind of a warmer house, 2 degrees outside, much cooler outside temperature. This would maybe be something like a winter type condition. And we're told here the length of our window is 1/2 of an inch, so similar to before. And converting that to meters would be about 0.0125 meters. So now that we have all of the variables we'll need to find the heat transfer rate, it's really a matter of solving algebraically. So here we go, 0.016 multiplied by 0.9 by 1.1 multiplied by 18 and divided by 0.0125. I get a value of about 22.81, and we could leave this in watts, but I'm going to write it as joules per second because time is something that we're focusing on here. So you'll notice right off the bat that number is significantly lower than what we found before, 1369. So we could just go ahead and say, well, that's definitely going to be a lower heat transfer rate, so much cheaper cost. But like before, let's go ahead and put some numbers to that and show how much of a lower cost. So as we did before, we want to take this rate in joules per second and scale that up to a month. So this would be really part F. E in the group problem is going to have you identify which of the model types is the best. So you'll look at models 1, 2, and 3 and then make a choice. Here in F, we're going to take our rate and scale that up to how much energy we lose per month. So 22.81 joules per second. As we mentioned earlier, we've got 60 seconds per 1 minute, 60 minutes per 1 hour, 24 hours per 1 day, and 30 days per 1 month. So we'll take our rate, 22.81, multiplied by 60, multiplied by 60, multiplied by 24, multiplied by 30. We're going to get, again, a pretty large number. Looks like 59, I'll just go and write this whole thing down just so I have it. 591,235,20. This would be joules per month. And again, what I could do here just to take care of the units, multiplied by 1 month. So I'm just looking at exactly how many joules of energy I'm losing. And then again, we have 10 windows. So the next part here, part G, we'll be just taking our value of how many joules we lose per month. I wrote that value down correctly, I believe I did. 59123, 520, good. How many joules we lose? Multiplied by 10. Remember the problem has us dealing with a house that has 10 windows. So multiplied by 10. We get really, number looks very similar, except now we've got one more zero there. So 591,235,200 joules. That's how much energy we lose just as a quantity. And then lastly, we want to figure out how much we're paying for the heat loss under these new conditions with the energy efficient window. So take my number. This would be part, that is H, last part here. And use the rate that we talked about earlier. So 591,235,200 joules. And we were told earlier that for every 10 to the 8 joules we use, that's going to cost us about $1. So now we will divide by 1 times 10 to the 8th. We get about $5.91, or $5.91. So as you notice, as we were doing this, the process looked very, very similar the second time around. We just found a new heat transfer rate for our new window, and then scaled that up to a month, and then used our rate to figure out how much money we would be spending. Now you'll notice here that number is much, much lower. Something that might be a little bit more realistic if we were dealing with something like an energy efficient type of window. You might also want to know that these windows actually aren't very cheap. Oftentimes they're very expensive to get the equipment, have them installed, but as you'll notice, over time, the money that you would save would ideally repay some of the money that you spent on the installation and the purchase of the new windows. So there's a bit of an investment that you would be making here. So hopefully this gets you going in the right direction, looking at group problem 7C, applying some of what we know about heat transfer rates to analyze something like windows and energy loss in a home. Okay? As always, if you have questions, don't hesitate to ask. I'm happy to answer those, and check Canvas for extra keys and resources. Good luck.